Welcome to the Databricks Skill Builder series. We're glad you're here.
Cool. Yeah, thanks, Stephanie. So yeah, today I wanted to talk a little bit about big data history. This is a presentation I was doing internally to my team, and we thought it would be a good one for this group as well, because it goes over a lot of the foundational technologies that Spark is built on, and it provides a lot of context for the issues that Spark solves, and also it's a good primer into the competitive landscape right now. So with a lot of the new features that are coming out, or a lot of the competition in the space, you can sort of see actually how these aren't anything new, that these themes have been coming up again and again over the last decade or so. And you can see sort of like how these different groups addressed these issues again and again. So I'll go ahead and jump into it. So the first thing is the rise of Hadoop. So Hadoop came out. Doug Cutting started working on Hadoop in 2004. And these sort of came out in response to some work at Google. So the idea was, the Google file system, which was basically this way to store things in a distributed manner that had sort of like a common interface. So this was basically like the predecessor to HDFS that we'll get into. Basically, what Hadoop was, if you haven't been exposed to it before, is Hadoop was how do you store everything on your on-prem servers, such that if any of those servers goes down, you're going to be fine. And you want to have a common interface. You don't want to have to keep track in your head of where everything is, and you want everything to be available. So this is sort of like what Hadoop came to start to address. And then on top of that, so in addition to having the file system, having having Google file system and then HDFS, also this idea of like MapReduce, there's a talk like MapReduce simplifying data processing on large clusters, which was huge, because the idea was, now that we have this data that's stored, how do we actually do some sort of processing on it? So, I mean, the algorithms that were created in MapReduce are sort of like the first rendition of what we're doing now in a very more sophisticated manner with Spark. But basically, these papers were first developed all Google, based on Google's internal data processing and infrastructure, which was indexing the internet. So it's definitely big data. So I already addressed this a little bit, but basically what was cool about Hadoop was that it was a nice command line interface that basically looked like a traditional directory structure, like POSIX, like directory structure. So the idea is that if it used to be, if you want to do really high performance operations and doing things at scale, you had to use a supercomputer, and a lot of universities had a supercomputer, a lot of companies had supercomputers, and it was like really, really high-end infrastructure. And it was really expensive machinery. The cool thing about Hadoop is it was designed for commodity hardware. So you could just, anything off the shelf that was relatively, cheap, you could use. And it was such that it was designed to fail. Like, if you have a data center that's 1,000 machines in it, you just assume that some small fraction of those machines are always going to be offline due to some issue. And that's sort of the assumption that Hadoop was built with, was that things are going to be going down constantly, and that fault tolerance, we see that in a lot of these other projects going on. It's actually, I'll go more into like Presto and Spark and something, things like that, but yeah, it was built for commodity hardware. you had 64 megabyte files only. Everything was sort of split up into those chunks. And then you would have 3x replicas of everything by default. You could set it to more, you could set it to less, but most of the time it was you had 3 replicas of every file, which was needed to achieve that fault tolerance and achieve the availability. Like if somebody was modifying something, you needed to make sure that that it could still be read and things like that. And there's a whole bunch of issues related to like that Hadoop solved about like, well, how do you make sure that a change to a file, replicates through the other replicas, so on and so forth, which not super useful to go into. But if you read like designing data intensive applications, they go like really deep into that sort of thing. But anyway, HDFS matured. The most mature version was HDFS 3, which sort of like achieved a lot of nice features like encryption zones, permissions, parity blocks. But yeah, you can see on the right there's sort of there's a depiction of how these work. So basically the idea is that each of your replicas would be on a separate machine. You wouldn't want to have your same replicas on the machine. That doesn't make sense. If the machine goes down, then you would lose everything. Instead, like in HDFS, it would actually, you would know like which of your machines were separate, like which of your drives were on different machines. And then even at the rack level, it's like, so if there was some power issue that affected the whole rack, you would be assured that your replicas would be on different racks. And and the big cloud providers are actually still doing things like that. It's just we don't have to worry about those these days since we're just like using the cloud. And so the other side of this is MapReduce. And so MapReduce is basically, okay, now you have everything stored on the cloud. How do you do processing on it? So there's like, this is from the command line. You would use like Hadoop job submit, and then you would give a file. And Stephanie was telling me actually she when she was at the DoD, she actually was writing MapReduce jobs. And basically how this worked is you would have, it's very similar to how Spark works under the hood. If it was a lot more naive, you'd basically write a bash code, or even down the line, it could be Java, and your bash code would be applied to all the files that are in storage, and then that would be like your map operation. So you'd have some code, it gets that gets applied to all of your files, and then there'd be a reduce operation. So the result of all that code would come back to one location, like just the master node, and it would do some sort of operation and then return the results. So like, for instance, if you were doing a word count, right, and you had a bunch of flat files, the map operation would be do a grep on all the files that are there, and each machine separately would do the count, and then the count would come back to the driver node, and then they would basically add it up. So that was like how like the MapReduce worked. And the scheduling algorithm at the time was very, very simple. It's just first in, first out. So I remember when I was using these algorithms, it was super annoying, because if you had one job going, you couldn't really do anything else until that job finished. And if there's something wrong with it, then you were completely just blocked, and then you would have just wasted a lot of time. That eventually, the scheduling evolved into Yarn, which was yet another resource negotiator. And I'll go more into that, but that problem did get solved and sort of opened the door for other applications in big data. And we have some architecture on the right. There was a bunch of different like servers that were part of like Hadoop's like MapReduce. So you'd like the job tracker, which tracked the job status. You had like the name node, which kept track of, okay, where is every file in the server farm. The secondary name node, which is basically, okay, let's say the name node fails. Now we don't know where anything is. No, we have a secondary name node that takes over with the first name node fails. And then there's a whole issue of like, well, how do you keep these two in sync if things are coming in really fast, right? And then you have the resource manager, node manager. These are like the ones that are actually in charge of scheduling and running the jobs on each of the nodes. Anyway, I won't go super far into that, but there was three main vendors. Oh, actually, I want to mention one thing about this. So these days, we make a really big emphasis on the separation of compute and storage. That's a new concept. Back then, it was you're doing compute and storage on the same machines, because if your machine had the file on it, then that's the machine that had the file on it. So you had to use it. And that was sort of like the way it worked. The way that we do it now is a lot more stable. So let's talk about some of the vendors. So this is sort of like, the sort of landscape back in the day. You had Cloudera, Hortonworks, and MapR. Cloudera was known for being sort of, I feel like it was, I don't want to say like, it was like the enterprise tier one. It was, in many ways, it led in terms of, Cloudera is still around. It had a lot of tooling, a lot of ML, definitely led in the ML area, the warehousing area, and analytics. So like Impala, like Kudu, those things it did really well. And then Hortonworks was definitely not the same sort of like enterprise ready, but what they were really known for is a really strong open source commitment. So I remember I could just go and download Hortonworks and install it for free, which was great. Like, with Ambari, their nice like UI to everything, it was nice. They also innovated. They had a really strong innovation, and they really went pretty far into like governance and management. So like, Apache Ranger and Atlas. Ranger is now Preface. That was like the spinoff company that all came out of Hortonworks. And then there was MapR. MapR was sort of like lone wolf. They were known for super high performance. They had their own fork of HDFS that was completely proprietary. And it was known to be like, it was a lot more knobs, things that you could tweak, but it was known to be a lot more advanced. They were the most, I would say, closed off in terms of the open source. And they had a lot of really like high performance products. And they were also known for like having like more advanced security features. So the way that it sort of worked out is Hortonworks and Cloudera eventually ended up merging in the face of like all the cloud providers sort of like eating their lunch, Databricks also coming out. These two sort of merged, and then MapR didn't survive. It's sort of a testament to, if you don't open source things, people don't really adopt them, and we'll go more into that with Impala. But yeah, the other thing is that with MapR, they had the really high performance alternative to HDFS, but even with high performance HDFS, eventually HDFS is not competitive anymore. So let's talk about the schedulers. So schedulers, like I was talking about, like first in first out, which is how MapReduce was, and it was super, it wasn't very nice, because the way that the space started to evolve is you actually wanted to have a lot of different applications that were on your Hadoop cluster doing various things. So like, you might be updating your like data warehouse, and you might be like running this MapReduce job in batch, and then you might be running this thing at the same time, and they all kind of need to like play nicely. So if you're just doing first in first out, which is what Job Tracker was doing in MapReduce, like that's just not going to cut it. So we needed a way to handle scheduling, and it needed to be fine-grained. So we needed like customizable resource allocations, application isolation. We wanted to make sure that some other applications going to steal a bunch of the resources, and we also need to handle like non-MapReduce workloads. So like any other sort of distributed program that was running needed to also compete for those resources, and of course it needed to be scalable. So Hadoop's Yarn was the sort of like was like the most like canonical scheduler. Yarn was yet another resource negotiator, and it was known for having a really tight integration within Hadoop. So we'll go into some of the things in the Hadoop ecosystem like HBase and of course like MapReduce, Spark, things like that, Pig. Yarn worked really seamlessly with all of those Hadoop based applications. And then eventually Yarn basically like was a part of Hadoop. It just like sort of came in like with Hadoop. It was part of Hadoop 2.0. And it sort of like became the backend for Hive and for Spark. So like when back in the day, if you were using Spark, you would say, okay, I'm using Yarn as my resource negotiator, as my scheduler, and it had a really tight integration with that. And then there's another project that was out of the UC Berkeley AMP Lab that Matej Zaharia, who created Spark, actually was working on initially, was Apache Mesos. So it was a team of which Matej was one. But the idea for Mesos was it was supposed to be a little bit more flexible. So the idea was, whereas like Yarn was really good for things in the Hadoop ecosystem, Mesos was a resource negotiator that could work for things outside of Hadoop and also in Hadoop. So things like, for instance, like Cassandra, or any sort of like non sort of Hadoop like database. You could, like a NoSQL database, you could link up with Mesos and be able to achieve all of that. Mesos was also known for it just had a better, more fine-grained access and a more advanced scheduling, multi-tenancy sort of capabilities. So you could do a lot more fine-grained like resource allocation, which is cool. I remember I started off using Yarn on my Hortonworks implementation. Eventually I was just like, it's not really cutting it. I'm not able to run, allocate my resources as nicely as I wanted to. So I remember at one point I was like, okay, I'm switching to Mesos for this. But anyway, Mesos didn't survive. I think Yarn improved enough to sort of outcompete it. And then of course, other technologies came out that sort of worked on that. But Yarn is still used, I guess, for people that are doing on-prem. So that's still there. The next part is running queries. So we had MapReduce, right? And MapReduce was, I told you a little bit about it. It was like pretty naive. Like you would be writing either your Java or your Bash code, and it would just like go send it over, get the results. Everything is, it wasn't like in memory by any means. It was all just like, everything was operating on files that are, cold files that are on disk. So the question sort of became like, well, how do we improve on this, right? Like, how do we query HDFS more effectively? So there's a lot of frameworks that sort of came out to address this, but I wanted to sort of like talk about these three because they're sort of like the more impactful ones today in the big data landscape. So Hive, and I'll go more into Hive. This was developed at Facebook and it was released into the Hadoop ecosystem. And what was really cool about Hive is, for the first time, if you wanted to do a query on files in HDFS, you could use a SQL-like language that was called HiveQL. A lot of people still use Hive. So what was cool about it is, like, I mean, it's kind of magic, right? Like you can write your SQL query and you can query a CSV, a TSV, Avro, JSON, Parquet, ORC eventually. You could write SQL to do all those things. So in the beginning, all Hive did is it took your SQL and it converted that into a MapReduce job and just ran the MapReduce. So it didn't actually have a better performance by any means, but it was so much easier to use that most people wanted to use it. Eventually, and I'll get into this, like Hive started to sort of like co-op different backends. So you could do like Hive on Spark, Hive on Tez, Hive on what have you, to be able to get more performance and actually do things faster. But initially it just ran a MapReduce job in the background. And so because it was using some sort of SQL dialect, it worked well like by creating like a metastore. So the Hive metastore is something that, Databricks still in our product, especially like up until Unity Catalog, the Hive metastore is essential to the way that Databricks works. The idea is that even though you have these files that are flat files, you want to store them in some sort of like database schema, catalog, whatever. So that's what Hive really did well, is now you can query flat files and you can just treat them like they're in a traditional database. There's external tables. And also it did partitioning too. So like you could set your partitioning scheme in Hive, and Hive would do a little bit of partition pruning and things like that based on your partitioning scheme. And then Apache Pig came out a little bit before that, and that was developed at Yahoo, which was a pretty big player in this space. And Pig isn't really used too much anymore. But what it did was pretty interesting. Is it had a SQL-like syntax that was called Pig Latin. It wasn't anything close to, like HiveQL was like at least a little bit close to ANSI SQL. Pig was like not. It was like completely separate, and it was like its own sort of mix of SQL and a programming language. And but basically you could write in this Pig Latin some pretty like complicated queries and run your jobs on HDFS using that. It also supported Java and Python UDFs, which was a first, which was really useful. But yeah, it had kind of a funny, like a funny dialect, like grunt, load, pig store, what have you. And then Apache Drill came out much later, 2015. But this one was actually developed at MapR. This was one of their eventual like contributions to open source, although it took them a long time to open source it. And it spun off the company Dremio, if you've heard of that one. They're really big in the in this space. The idea is like other ones, a SQL syntax. It did, and the cool thing about it is it did schema inference. So for Hive and Pig, if you wanted to read a file, you had to basically say, this is my schema, read it into my schema. Drill was cool because it would actually infer the schema and read that for you. So you didn't have to like do that extra step. And of course, it comes with its own challenges, but it was pretty cool. And it worked well with not only Hadoop, but also like NoSQL databases and cloud storage. So it was like considered like pretty interoperable. So yeah, Apache Pig didn't really survive. I'm sure some people still use it, but it's Spark is definitely eating its lunch. And now let's go into sort of like those storage formats that were on HDFS. So when we're talking about like, when we're talking about, Hive, Hive is querying like your TSV files, CSV files, but also could do more. So what were all those sort of files and how did they come out? So at the beginning, 2006, it was rough. Like, it was pretty much just text files like CSVs and these .har files. I forget what har stands for, but these were like really, I think it was like high availability. I mean, let's skip that one for now, but it was pretty slow. Everything was in these super unoptimized file formats. I mean, if you think about it, like if you're trying to parse through files that are not serialized, they don't have any sort of like easy structure to look for things. It's just going to be slow. You have to do a lot more like full table scans to get any sort of results. In 2007, as part of a new Hadoop version, Hadoop sequence files came out. Those were a little bit better. They were flat files still, but they consisted of binary key value pairs. And they were used in MapReduce jobs to sort of like aggregate small files. So the canonical problem in big data is dealing with the small files issue, right? Like you're writing a lot of small files. Number one, like whatever service is keeping track of where all those files are is going to get overwhelmed. And then also you don't know like which files you need and which files you don't need. So you just have to look through all of them. It's really hard to do some sort of like, partition pruning or filtering. So these small files provide issues. And so the sequence file would aggregate these small files and then sort of turn it into these key value pairs. That would be a lot faster for MapReduce to look at. Then you had HFile. That was in Hadoop's like first NoSQL database. And then that was Apache HBase uses these like these H files. 2010 Avro came out, and Avro has been pretty awesome. A lot of people use Avro. Databricks customers use Avro all the time. I see it. The thing that was different about Avro was that it was row based and it supported binary JSON format, which is cool, and it also supported schema evolution. So I'm sure a lot of you guys are familiar with Avro, but yeah, it's been out for quite some time. In 2013, Parquet came out. Parquet was, of course, a game changer. That was sort of like it underlies like Delta, Iceberg, so many different technologies. What Parquet does is it does the same thing that Avro does, in which it can support like nested schemas, but it was column oriented instead. The cool thing about column oriented is it makes it a lot easier to do like partition pruning or predicate pushdown. So you can easily just like search inside of one column for exactly the thing that you need and pull that out. And then of course, with Delta later on, you can actually store a lot more metadata about that. And then Apache ORC also came out. That was developed by Hortonworks. Apache ORC was special because it supported like built-in indexes, and it was also column oriented. Apache ORC was really was really an optimization for Hive. Like the suggested usage with Hive was to use ORC files as the base. So convert all of your CSV, TSV into ORC files. So I think people still do use ORC if they have a Hive heavy workload, but it's definitely not as popular as it used to be. And Parquet seems to be a lot more ubiquitous, versus ORC was mainly optimized just for the Hive sort of use case. So I just want to pause for a second. Does anybody have questions? Okay, I'll move on. Hearing none. So going into Apache Hive. Yeah, I just wanted to really touch on Apache Hive more because it's been such a iconic part of the big data landscape. What it did initially was a game changer, and even though it's definitely like fallen out of favor today, it's kind of like a nice it's a nice example of like the essence of the evolution of big data and sort of like what were the issues it solved and the way that it proceeded. So like I said, when it was first released in 2008, it just ran MapReduce queries, and it allowed you to do that on arbitrary files in HDFS with a SQL interface. So it said like, I have a database, but I don't actually store anything. It's like Airbnb. Like we do rental bookings, but we don't own any rental properties. It's like that. Like it looked like a database, but it just translated your SQL into MapReduce jobs and ran those things. And then 2009, it produced UDFs. I think everybody could see like why UDFs were going to be useful. Like there's only so much you could do with the SQL statements. If you want to do something more complex, use Java, then you would want to have UDFs. And that was a really big game changer at the time. 2010, they added partitions and bucketing. Partitions, of course, became super important in Hadoop and in the entire space. So, I mean, the way that the Hive partitions worked is really similar to the way that Spark did partitioning up until very recently. So, basically, and this might be a review, but basically, like you have different, like for each column, like if you want to partition on month, you would have your directory is called month equals 06. And so all those like June files are going to be all in that one directory. And at the time, that was really nice because then if you had your query and you queried on month, it would just go look in that one. That's like partition pruning, right? And then bucketing was similar. It was just like, you would, if you had something that's more high cardinality, you could just bucket it. You could just take it and put it into separate things. And then it would be a lot faster for queries just to only touch the buckets that needed it. In bucketing, they tried to bring into Spark, and I mean, it wasn't Spark for some time, but it's really hard to tune it to do the performance. So we don't really use it anymore. Actually, with like, yeah, with new features coming out, we're going to be sort of like readdressing some of these things. You have to be at Summit to hear about those. They're really exciting. Okay, and then 2014, Tez and Parquet came out. So Tez was basically, so up until then, they were running everything on MapReduce jobs in the background, but Tez was sort of a more like in-memory way to run jobs on Hadoop on like HDFS files. So with Tez now, like you would use Tez instead of MapReduce. And I remember like I would run it and it says Tez is doing this. And I was like, wow, Tez so much faster. That's great. Of course, it was still super slow compared to what we have today, but at the time, it was a really big upgrade. And Apache Tez was its own project. But yeah, we got more fine-grained control over the execution of jobs. It interacted better with schedulers, and it was much faster than the MapReduce. And then also Parquet was supported there because Parquet came out, and as a storage format, up until then, they were just running things on flat files. So that wasn't super performant. With Parquet, it's a serialized data format, it's column oriented. So a lot of benefits there. And then 2015, we got Hadoop, Hive version 1, and that also came out with ORC. And ORC was sort of like this better version of Parquet. It was like a lot of it was similar, but it was optimized just for Hive. And then 2016, version 2 and LLP came out, and LLAP was, it's an acronym. It replaced Tez basically, and it stood for either low latency analytic processing or live long in process. I saw it both ways. I think it was kind of just like a funny thing. But basically the idea was LLAP, which was a lot faster than Tez, allowed for like sub-second query latencies, and did a lot more caching, and it held a lot more in memory. So these days LLAP would be slow, like definitely slow. But at the time, I remember when I first ran LLAP, I was so impressed. I was like, wow, what a big change. And LLAP, Spark was really the first technology to start doing a lot in memory, and LLAP sort of like copied that idea. Okay, so those were sort of, that was Hive, and we talked about some of the query engines that Hive sat on. but I wanted to just go through all of the sort of like query engines, and what they, the different like differentiators between them. So Apache Spark actually is relatively old in the space. Even though like we still use it today, it's not one of the more recent ones that came out. So it's developed by Matei, and of course, like the crew started Databricks a few years later, based on just Apache Spark. And the cool thing about it is, it was the idea was with Spark was it was a general purpose distributed processing framework. So the idea is that you could take whatever use case you wanted and just sort of pop it onto it. And it was also really, really heavily open source focused. So a lot of companies would just, because it came out so early, it got a lot of nice connectors added to it early, and it sort of like had that sort of like momentum. It was still rough to use back in the day, like don't get me wrong, but it did what it did, like very well. And then because I guess Databricks was behind a lot of the innovation, it kept up with the times really nicely, whereas some of these others did not. So it also supported ML, which was not something that was supported in like, let's say, Hive. And it was really tough to do that stuff with like MapReduce jobs. It was in-memory processing. And the one thing about Spark that other technologies tried to optimize on, which I think is still room for improvement, is Spark was sort of like fault tolerant to a fault. It's like fault tolerant to a fault. So the idea is that fault tolerant is super important. If your node goes down, you don't want your job to stop, but the overhead associated with making that happen causes a lot of issues in the code. So like when we look at technologies today, like DuckDB or like even Presto, which is like not fault tolerant, they're sort of just designed to be super, super low overhead code. So if you run those, they fail, you just run it again, that's fine. It failed before. Spark was really designed for these like long batch jobs back in the day, because that's how everything was back then. And you didn't want it to fail. You wanted to just like self-recover if something went wrong. But because of that, it was slower back in the day. Is there a question? Okay, moving on. So then Apache and Pollock also was a query engine that worked under the hood. This was a faster alternative to Hive, and this was a Cloudera only product for a long time. It's actually arguably one of the reasons why it didn't stick around, is because they didn't open source it fast enough. It was designed to be used with these tables that are called kudu tables. So there's another sort of like proprietary thing that Cloudera had. And it was designed for more ad hoc and complex queries. And eventually it just didn't really have the open source contribution it needed. So after many years, they tried to open source it, but it was a little bit too late and it eventually died. But it was, at the time, it was a very, very performant like alternative to Hive that did like sort of that low latency like analytic processing like really well. Presto also came out. It's now called Trino. And that was developed at Facebook. Facebook still uses it. A lot of folks, I think, who are on-prem, like some of the like I think like maybe like Lyft uses Presto. It was sort of like, you can think of it as sort of like a better version of like the Hive like processing. It's very much like very SQL focused. It doesn't really do a lot of like ML stuff. It was really best for like BI queries, and it was designed to really be good with ORC. Like I said before, it had lower overhead, so it's not as fault tolerant, but because of that, it had some other advantages. Apache Phoenix was developed by Salesforce, and it was sort of like a Hortonworks tool. That was also, it sort of like was the Hortonworks answer to Apache Impala. It was a fast alternative to Hive, but instead of being used with a Kudu backend, it was designed to be used with HBase. And HBase was sort of, I didn't really go into it before, but it was like the database that sat on HDFS on Hadoop. And Apache Phoenix was really good for like read heavy workloads, where Impala was better for like more like ad hoc or like complex queries. And then Apache Tez, which also I mentioned, was sort of like this this addition to Hive that was just known to be a little bit faster than MapReduce, and could be used with HDFS, HBase, Cassandra, and Kafka. So there's like different sources for it, you know, as well. Okay, so let's shift gears a little bit. So far we've been talking about mostly just like the Hadoop ecosystem, but it's important to go into the NoSQL databases. And a lot of these NoSQL databases actually predated a lot of the Hadoop ones. So for instance, if you look at like CouchDB, MongoDB, these came out like very early on, like in the mid 2000s. These were not really initially associated with HDFS, but they integrated with it later on. The idea with these is that there are key value stores, they're document databases. And I'm sure everybody's familiar with like document databases and what they're good for, but it's like every record is like sort of like a primary key, and you can just filter to that one. So the idea is your lookup time is super fast, because if everything's a primary key, it's basically, think of it as like a big hash map that's like in the cloud. So there's like constant time lookup for any document that you're trying to get. So, even today, even though CouchDB isn't as popular as it used to be, MongoDB and some of the spin-offs that came out of it, like Cosmos DB, are very useful, because like if you have a table in Spark and you're trying to query some like one record, you might have a hard time getting that one, versus in MongoDB it's all like it's stored as constant time lookup, so you can just go to that one record really quickly, get the document, any nested JSON in there, and bring it back. Apache Kudu, which I mentioned before, was Cloudera's like analytical storage engine. So that this was like it was column oriented. It was really good for doing like updates. It was really fast with that, but it wasn't really in like ACID. Like it didn't do transactions like as well. And then it also had a pretty simple data model. Like I think these days everybody expects nesting is supported. It didn't really have that. So yeah, this is one of those that just didn't really, unfortunately, didn't survive so much. Cassandra has been a pretty major force. This was Facebook's invention. It powered Facebook's index inbox search. So it's also column oriented. It allowed you to do like structured and semi-structured data, high availability. It was really good for like read heavy workloads. So yeah, if you think about like like querying your inbox, like you've used Cassandra's like so many times if you've used Facebook before. But that sort of like use case was really good for. Also, Spotify uses Cassandra. It has a lot of features that allows you to be like just geographically distributed. And the way that it does things under the hood, so like because it's you have to do replications, especially with geographic replications of data, like everything needs to be stored like so many copies of it. The way that Cassandra approached how information trickles to all the replicas was actually pretty novel at the time. It had a what's called like a no leader replication. So what would happen is like your different machines would, they call it like gossiping. They would like gossip with each other, and they can communicate the changes through this like gossiping network. Again, like that stuff is really interesting, but you have to read the designing data intensive applications to to learn more about that. And then, of course, I also wanted to mention Apache HBase, which was the sort of like NoSQL database that was built for Hadoop. And Apache HBase was used quite a bit. It was behind a lot of the larger like tech companies' products. And yeah, it supported like complex data models, and its H file format was a serialized file format. Okay, so let's talk a little bit about streaming. So the first really big thing for streaming that came out. So back in like the mid 2000s, streaming wasn't really on people's radar. The way that most people did things was large batch jobs. And the idea was, everything was on flat files, right? So it's going to take a super long time. Like nothing was like in memory. The idea was that you would just run a batch job overnight and it would like re-index everything and, retrain the way that Google did its search engine, like re-index the entire internet. And that would just happen. It would take a long time. It would just happen. Everything was just batch. But the first big application of it was actually how do you keep those logs in some sort of centralized location? Because if you have a bunch of batch jobs running and they're spitting out to different like log files, then like how do you collect those into some consistent space? So the first big application was Apache Flume, and this was supposed to be a distributed, reliable system for moving logs into Hadoop. So the idea is like, it's on these different systems and you just want to stream it all into Hadoop, onto HDFS so that you can query it and see if anything went wrong or call your metrics, whatever. Kafka came out soon afterwards. Kafka is another one that, came out only a year after Hadoop. A year after Spark. And it's really become a really important technology. Confluent's been crushing. So Kafka, high throughput distributed message system. I'm pretty sure everybody's familiar with Kafka. And it's sort of like a leverage to pub sub model. So you like subscribe to the topic, the broker would like give you what you need. Apache Storm was the first like distributed like real-time like streaming service on Hadoop that was not meant for just like logs. So the idea is that it would use like a tuple data model and it would stream these tuples. So it's a lot more similar to, I guess, the way that Flink works, because it's real time. The way that Spark streaming was working is that it's more like a micro batch. I mean, everything, if you break it down to its fundamental elements, is some type of micro batch. But Apache Storm was, and I believe it's still used, is sort of like a streaming application. Spark streaming, this was like a new feature in Spark that came out in 2013. The idea, first it was D-Streams. It was Tagatha Das, who works at Databricks, worked on it as part of his PhD. The idea was that we would use the same sort of Spark APIs, and then just add on streaming to it. So that's like, Spark initially was just like this reusable template. And then you could have features like this built onto it. And the idea was that if you used a micro batch model, you could just have a bunch of micro batch jobs. And that's the way that Spark Streaming started. And then Flink came out 2014. It was a project called Stratosphere before that, but there were some copyright issues. They weren't allowed to use the name Stratosphere. And Flink is still used pretty heavily today. It was known to be like a batch-end streaming system, but the APIs for batch-end streaming were somewhat different. I don't want to, I would say Flink, you could say it competes with Spark streaming, but so I don't want to say like too much about it, but basically the idea is that it's like Apache Storm, it's more real time. It doesn't really use that micro batch architecture that is fairly central in Spark streaming. Its API is a little bit more cumbersome for people. So it's a lot easier for people. Nobody really uses Flink for batch anymore. That's something that came out initially, and then they sort of added on streaming, and then now it's sort of like mostly about streaming. People usually have a hard time with it just because you have to like learn this whole new framework, versus if you're already doing your batch jobs in Spark, you just change a few lines of code and then you're doing Spark streaming. Yeah, so I would say that Flume and a Storm aren't used as much anymore, but Kafka, Spark Streaming, and Flink are. This is my last slide, and then I'm happy to take some questions. Want to go a little bit into security. Kerberos was sort of what was being used beforehand. It's not really like a Hadoop thing, but it was sort of like when we were laying like the foundation of where security was before. Everybody was using Kerberos. It was the idea is that you would have these like sort of like Kerberos tickets, and you would be granted a Kerberos ticket, and then that would allow you to go do something. It was born out of MIT, and it was like really central to the whole Microsoft ecosystem. But yeah, you would do like K in it, and that would like create your Kerberos ticket, and then you would have your identity specified in your ticket. So this was like, you know, one of the big like things that was happening at the beginning, and then other technologies came out. So like Ranger and Atlas were more popular for like the Hortonwork users, and then Apache Knox and I believe Sentry were more like Cloudera. Apache Knox was like application REST API, and it was not as much about security as more about operations and developer adoption of the ecosystem. And then Sentry really provided that sort of like role-based group, RBAC, but it was for Hive and Impala, and it worked with Kerberos. And it eventually did get deprecated when Clutter and Hortonworks merged. Apache Ranger was born out of Hortonworks, provide the same like RBAC for Hive and Tez. So it allowed you to sort of like, you know, give limitations to your users who are mostly doing Hive queries. And basically when Clutter and Hortonworks merged, they chose Apache Ranger over Sentry. And then Apache Atlas was more for like overview, like things like seeing everything that's there, governance and things like that. So yeah, this was my last slide. I wasn't sure whether to include it, but basically the idea is like Spark really did sort of take dominance in this area because it slowly sort of evolved to handle all of these different use cases. And it sort of evolved with big data. So like now streaming is really important. Batch jobs are still being used, but that's not like, we have good solutions for those. Streaming is now like a big area, and Spark has grown really elegantly into that area. But the idea here is that a lot of the things that Spark does, like lazy evaluation, transformations and actions, DAG-based execution, and memory compute, these all existed in previous projects. Like, you know, Pig had that. Even like with you know, a big thing about Spark 2 is like running ML. Like Mahout was an open source project before that actually did that, and was sort of like that was co-opted into Spark, and became, it was a predecessor of Spark's like MLlib, which was like is now deprecated in Spark. We have a better one now, but it was important at the time. And then yeah, a lot of these the ideas that came to Spark like did already exist before. So anyway, I don't think I have a conclusion slide, but I'm happy to take any questions. We have about 4 minutes left. Cool.
Well, it looks like we don't have any questions, but this was really great. I really enjoyed this. Thanks, Dan. And everybody else for joining. Everybody have a good day.
Cool. All right. Well, thank you. Good chatting.